Hey you guys, good afternoon, good evening, good morning, wherever you are. Welcome back to the Math Fun Room. In today's video, I want to discuss with you implicit differentiation. So, real quick, conceptually, the purpose or the reason why we would need this technique is when we can't describe our curve or our function explicitly as a function of x. So what does an explicit formula mean? So if I have y equals x squared minus 2x, that's y being explicitly defined as a function of x. I could have y equals, sine of x times e to the x. Y is explicitly defined as a function of x, right? And a lot of times we use symbolic notation, like where we say f of x equals, sine of x, e to the x. Now, there are curves and equations where we may not be able to solve to get y as a function of x. So for example, if I had x cubed plus y cubed equals 6xy. So here's an equation where y is not defined explicitly as a function of x. And if I tried to do some algebra to solve for y, this would be pretty impossible. In this case, it might even be impossible to use algebraic techniques that we know up to this point. So the idea behind an implicit differentiation technique is we want to be able to go ahead and find the rate of change of this curve or the slope of the tangent to that curve. And even though we don't have y as a function of x, we should be able to accomplish finding the rate of change of that curve. So to look at a couple graphs real quick to just discuss this momentarily. So here is a curve, x cubed plus y cubed equals 6xy, that I cannot solve for y to get it in an explicit form. This equation describes this curve implicitly, right? So this is an implicit equation where y is not defined explicitly as a function of x. And we can see that on this curve, this is a nice, smooth, continuous curve here. It definitely has a derivative that appears to be defined everywhere. Right? It looks like about right here at 2.5-ish maybe, there's a horizontal tangent. Right, so at any point that I pick here, let's say x equals 1, there's a slope of a curve here. In fact, there's two parts of the curve that have slope, and in fact, there's three parts of the curve, right? So because this graph is not a function of x, then it's failing the vertical line test. And me picking x equals 1, there are 1, 2, 3 points of tangency that we could discuss. All right, anyway, so the technique that we're discussing in this section is how could we go ahead and find the slope to this curve for any value of x. So we want to find its derivative. Just to take a look at a couple other cool looking graphs, here's an implicit curve. This is sometimes called a cardioid. Right? And then here's another implicit curve, sometimes called a lemniscate. I love this one because it looks like an infinity. Right? So something else I want to mention to you as well, right? And I can look at this, let me come back to this graph. So when we look at an implicit curve, just like sometimes can happen with an explicit function, if I look at an implicit function, notice that we have a corner here at the origin. So keep in mind what we talked about when we had explicit equations, functions of x, we could also have corners, like an absolute value graph has a corner. So the derivative is undefined at a corner. The derivative is also undefined at an asymptote. What we're going to also know for, we're going to notice for implicit curves is we could have a vertical tangent. So check it out over here at x equals 1, we have a tangent that would be vertical. So the slope is undefined there, right? Vertical lines have slopes that are not defined. So our derivative would be undefined at x equals 1 for this particular graph. Our derivative would be undefined at x equals 0 as well. We can see on this graph we would have a vertical tangent out here at the ends, so my derivative would be undefined there in that case. And do we have one like that here? We'll check that out. We sure do. So it looks like right at the origin, as the curve comes into the origin here, we're getting a vertical tangent that is the y-axis. So anyway, so as we move forward into some other conversations where we look at implicit curves, those points where the derivative is undefined might be of interest to us. Okay, so now that we've discussed conceptually why we would need implicit differentiation, now let's focus on the skill. So what does the skill of implicit differentiation look like, right? In other words, how do I find, y prime from this equation? How do I find dy dx from that equation? So in all of those graphs that we looked at, right, our slopes are still delta y's over delta x's. We still had slopes of tangents that were being described as like rise over run, right? So if I look at, this particular slope here, the horizontal's tangent, the tangent is horizontal, and so my rise is 0. So I have a 0 tangent. I have a rise over run. So I'm still talking about a delta y over delta x in all of these problems. I'm still wanting to find a dy over dx. Right? So what's the derivative? So how do I get dy dx? How do I get y prime out of this equation? All right, so let's talk about how we would go through that procedurally. So first of all, I want to go ahead and just attack that equation. And then I want to come back and talk about some things in regards to the idea, right, of why we do what I'm about to show you, right? So I'm looking for dy dx. I'm looking for dy dx in this equation, what we wrote here. So what I need to do then is differentiate the equation with respect to x. So I'm going to use the differential operator to denote that I'm going to take the derivative with respect to x of both sides of this equation. So again, this is saying I'm taking the derivative of this expression with respect to this variable. Taking the derivative of this expression with respect to this variable, the x variable. So let's see what that looks like for a moment, and then I'm going to come back and discuss a little bit more and remind us of the chain rule. Now when I'm differentiating x cubed plus y cubed, right? I mean technically I'm taking the derivative of a sum, which is the sum of the derivatives. And then over here, I'm going to pull the 6 out, and I'm going to focus on the idea that we have a product there. Right, so using rules of derivatives, and this could be the next step that I take here. And eventually we want to become efficient, where we don't have to write that step. We just want to think it. But I just want to put in as many details here as we can for our conversation. Now, when we differentiate x cubed, that's going to be just a straight old derivative like we've been doing up to this point. Now, when I differentiate y cubed, this gets a little bit weird. And here's where it gets weird, and we'll discuss this in a little more detail at this moment here. So how do I differentiate y cubed with respect to x? And remember, we're assuming that y is a function of x, right? If I could have, in this equation, if I could have solved for y, I would be getting y as a function of x. Now, granted, we couldn't find y as a function of x, but we're assuming that we could. So what I'm really looking at in this expression is I'm looking at some function of x that's being cubed. And I want the derivative of that expression. So let me flip back to blue here, right? I'm finding the derivative of y cubed. Now when I do that derivative, this is a chain rule, right? So the outer function is the cube, the inner function is whatever this equation is. This equation could be sine of x, right? This could be sine of x cubed. This could be e to the x cubed, right? So whatever this equation is, the function is the inside, the cube is the outside. So I differentiate the outer first, bring the 3 down, take 1 away. And then the chain rule says multiply by the derivative of the inside. So what's the derivative of f of x? Well, it's f prime of x. That's what its derivative is. So this is the implicit part of our derivative. We're differentiating y cubed with respect to the x variable. We don't know what y is in terms of x, but we know that whatever it is, we could describe it as a function of x. Right? So mentally I'm replacing y with f of x, and to point out that we're doing a chain rule here. Now I'm going to come back and finish this in just a moment, but I'm going to pick a different color here to just kind of illustrate a little bit deeper what we're doing with this. Right? So let's pretend somehow we know that the f of x was, sine. Let's pretend somehow we know that the f of x is sine. So my y equals sine of x, or my f of x equals sine of x. How would I differentiate this expression? Well, again, this would be a chain rule. The outer is the cube, the inner is the sine function. What's the derivative of the outer? 3 sine squared. And then what's the derivative of the inside? It's cosine. So what we're doing over here is the exact same process. I just don't know what the inside is, right? The inside isn't necessarily sine of x, it's just some function f of x. So how do we differentiate f cubed? We do the derivative of the outside, 3 times that thing squared, and then times the derivative of the inside. So again, because we don't know what the inside is, to determine its derivative, we're just going to write its derivative as f prime. And that's the implicit differentiation, not knowing exactly what the function is inside. And again, the reason we don't know the function inside is because we can't solve for y here. So we're saying, well, it is some function. We're going to use the chain rule to take its derivative. So there's the implicit piece. Now I've gotten off track. I've gone on a tangent. Pun intended there, right? And I want to come back and finish this actual problem we were working on. So if I come back and look at this line here, right, we had the derivative of x cubed plus the derivative of y cubed equals 6 times the derivative of xy. So again, I'm going to point out to you real quick before I finish this. Here is x cubed, and I'm differentiating with respect to x. That's just a plain old derivative like we've done all the way up to this point. Here I'm differentiating the y variable with respect to x, and that's going to involve the implicit chain rule that we see here. Now when I differentiate this x with respect to x, that's a straight old derivative, and when I differentiate this y with respect to x, there's an implicit form. Okay, so I just wanted to pause the video for a moment to just kind of recopy this equation where we left off. So where we had left off was we took the derivative of 3x squared, of x cubed, and that was 3x squared. We wrote this guy right here as the derivative of f of x cubed, right? And we said that that was 3 times, man, my fingers don't want to work today, 3 f of x squared times f prime. So we have 3x squared plus, this is what we did right before I paused the video. Right? Now when we look over here, we really have a product rule. So I'm going to do, let's say, derivative of the first times the second plus first times derivative of the second. So I'm going to do derivative of the first times the second, and then plus first times derivative of the second. So we have a product rule going on there as well. Now, just like we did over here, I want to point something out to you, kind of like a mental shortcut. How did I take the derivative of this expression? Well, basically, let me come back up here for a second. What we did was we took the derivative like normal, and we brought the 3 down and took 1 away. So we're going to take the derivative like normal, bring the 3 down, take 1 away, and then we multiply by the derivative of the inside. We multiply by the derivative of the inside. So when I do these over here, I'm going to think in that same manner. So first of all, what is the derivative of x with respect to x? Well, that's just 1. And then what's the derivative of y with respect to x? Well, if I take the derivative of y, that's the same thing as taking the derivative of x. Derivative of y is 1, and then I have to multiply by the derivative of the inside. So there's my implicit rule. So again, kind of a mental shortcut is like back up here, right? When I take the derivative of an x variable with respect to x, that's just a straightforward derivative. When I take the derivative of a y variable with respect to x, that's a chain rule. That's implicit differentiation. So I differentiate y cubed as 3y squared and then times y prime. So I could write this in a little bit more of a convenient notation in that manner. So when I come over here and I differentiate, again, I differentiate x with respect to x, that's just a straightforward derivative. When I differentiate y with respect to x, I'm going to differentiate this like normal, derivative of y. is 1, right? Just like the derivative of x is 1. And then I multiply by y prime. That's the chain rule that I have there. And technically, here's my derivative. I'm done with my derivative. I have 3x squared plus 3y squared y prime. And then I'm going to go ahead and distribute the 6. So I'm done with all of my differentiation. Here's my derivative. Now, typically what you would see in a calculus textbook at this point is we would go ahead and solve for y prime. So we're going to do a little bit of algebra and solve for y prime here. And again, the reason we're doing that is because we're looking for dy dx, right? So what we want is dy dx. That's the same thing as y prime with our lazy prime notation. So here's the Leibniz notation, here's the prime notation. So we're going to do a little bit of algebra and we're just going to solve for y prime. So what I'm going to do is subtract this to the other side. I have 3x squared plus 3y squared y prime, and I'm going to subtract this term to the other side. And then I want the y primes by themselves, so I'm going to take the 3x squared term and subtract it to the other side. So at this point, I've isolated the y primes on the same side of my equation. So to finish off the algebra here, I'm going to factor out the y prime term. So I'm going to take this y prime term that's common between both of those terms on the left-hand side. And then the advantage of factoring the y prime term out is now I can isolate it, right? So y prime is multiplied by this thing, this factor, and I'm going to divide this factor over to the other side. So I'm going to have 6y minus 3x squared over 3y squared minus 6x. And there is kind of my final answer of the derivative of this function that we started with. I'm going to make this 2 a little bit prettier over here. So again, we started with x cubed plus y cubed equals 6xy, and we went through this process that we call implicit differentiation to find y prime. And here is us solving for y prime. Here is y prime. Now again, why did we use implicit differentiation? Because my function isn't explicitly defined as a function of x, right? Y is not explicitly defined as a function of x. It's implicitly defined in this equation. So we use implicit differentiation to find y prime. Now something to point out to you here, which maybe is obvious, maybe it isn't. Because we don't have y explicitly as a function of x, then y prime will not be explicitly a function of x. Notice that y prime has y's and x's in it, right? Has y's and x's in it. So no surprise there, right? The function y is not described explicitly as a function of x, so y prime won't be either. Okay, so I'm going to go ahead and let's build on this example here. So remember that this is the equation that gives me the slopes of the tangent lines to my curve that I have here. So my curve is x cubed plus y cubed equals 6xy. This equation allows me to calculate the slope of every tangent to this curve. So if we bring our graph back up, right, here was the curve that we were talking about that we just took the derivative of. So again, I could use that formula to find the slope of every tangent. Any tangent on this curve, that formula for y prime finds the slope for me at any particular point. And what I want to do in this particular case, notice that looks like right here, 3, 3. So if x is 3 and y is 3, that is a point on the graph. So I'm going to find, if I draw a tangent here, I want to find the slope of that tangent at the ordered pair 3, 3. So that's what I want to tack on to this example here. So let's go ahead then and find the slope of the tangent at 3, 3. So let's say we're doing like part B here, right? Let's find the slope of the tangent to x cubed plus y cubed equals 6xy at the point 3, 3. Okay, and again, we've really done the bulk of the work, right? The slope of the tangent comes from the derivative, and we have the derivative. So what we really want to do in this case, right, is we want to evaluate. We want to plug the point in. We want to evaluate y prime at, x equals 3, comma, y equals 3. So really, we're just going to come back up to our equation, and we're going to plug in those coordinates. We're going to plug 3 in for the x. We're going to plug 3 in for the y. So we're going to have y equals, and I'm going to plug 3 in for the x and 3 in for the y. So I'm going to 6 times 3 minus 3 times, and the x is also 3 over. And then I have 3 times, right, the y is 3 minus 6 times the x, that is also 3. So when I crunch this number, that gives me the slope of the tangent to that curve at the point 3, 3. Now, if I were to go through the arithmetic there, I'm going to get a slope of -1. Okay, so I just wanted to tack onto that example, point out to you that we are using implicit differentiation to find the slope of a tangent. And as long as we have the ordered pair, the x and the y ordered pair, we can find the slope of the tangent at any given point on that curve. All right, and then real quick, right, visually, one thing we had talked about was this graph in particular has a place where the tangent is horizontal here. So the derivative would equal 0, slope is 0. We have a point right here at the origin as the graph comes in this direction where the tangent is vertical. So the slope is undefined. So one thing we could do, when we won't do in this section, but one thing we could do in the future is we could find where the slope is 0. We could find where the slope is undefined. And when you think in terms of a fraction, right, where does the fraction equal 0? Well, that's where the numerator equals 0. And that would give us the points where the tangent's horizontal. We would set 6y minus 3x squared equal to 0. And if I'm looking for where the slope is undefined, right, the tangent is vertical, I would be taking the denominator. Division by 0 is undefined. I would set that equal to 0, and I would solve that equation. Now, that's a little bit more beyond what we really want to do in this section, so we're not going to do that, but just to have that conversation with you real quick. What we will do in this section is we will practice this process of implicit differentiation, right, finding y prime, and then we will plug a point in to find the slope at any particular point. All right, so here's what I want to do at this point. Now that we've discussed kind of visually, right, graphically, what an implicit derivative gives me, we looked at one example where we went through the skill of doing the implicit derivative, and we talked about the chain rule. Chain rule is really what gives us the workaround of the the implicit equation. So I just want to get a little bit more practice of doing the skill of the implicit derivative. So let's just throw some curves up here and let's take derivatives of these equations. So let's say I have the equation x over y plus 5x minus 3y equals sine of x plus cosine of y. I'm just making curves up here. I have no idea what this graph would look like. I don't want to dwell on that at this moment. Just want to practice the skill. So the instruction typically on a homework problem would say something like find dy dx. Right? Again, we assume if we could solve for y, that y is a function of x, and what we want to find is dy dx, right? Or y prime, if we want to use prime notation. Again, I'm going to take one step here, and I'm going to point out, right, that in order to find dy dx, we have to differentiate the left-hand side. We have to differentiate the right-hand side. So I'm going to differentiate everything on the left-hand side, and then I'm going to differentiate everything on the right-hand side. Again, I'm differentiating with respect to x because I want dy dx. So that's the order of my derivative in regards to the variable x. So we're treating y as the dependent variable and x as the independent variable, right? That's what Leibniz notation tells us. I really like Leibniz notation because it communicates that to us very clearly. Y is the dependent, x is the independent. So we're finding the derivative where we're thinking of y as a function of x. We get lazy and we use prime notation to just not have to write the Leibniz. Right? But the Leibniz indicates to us we want to find the derivative with respect to x, and that's why I'm choosing that differential operator. Now when I look at this first term here, this is going to be a quotient rule. So when I do the quotient rule, I'm going to have bottom and then times the derivative of the top, and I'm going to write this out, minus top and then times derivative of the bottom all over the bottom squared. And then let me just go ahead and do these derivatives. What's the derivative of 5x with respect to x? Well, that's just 5. And then what's the derivative of 3y with respect to x? So I'm going to just take the derivative like normal. The derivative of 3y would be 3. And then times the derivative of the inside. And there's my y prime term. Again, that's the chain rule coming from the implicit derivative that we discussed earlier. Now on the right hand side, I'm going to differentiate sine of x with respect to x. That's just a straightforward derivative like we've been doing up to this point. And then here's implicit. So the derivative of a y variable with respect to x, I'm going to take the derivative just like normal. Derivative of cosine is negative sine of y, and then times the derivative of the inside, times y prime. So at this point, I'm almost done with my derivative, and the reason that I'm not done with my derivative is I didn't finish working through the quotient rule. So let's finish off this quotient rule. So what's the derivative of x with respect to x? That's just 1, right? And then what's the derivative of y with respect to x? So the derivative of y would be 1 and then times y prime. Again, I'm being redundant writing these ones here. And the reason that I'm doing that is just for our conversation. So at some point, I want to get efficient. I want to become efficient and stop writing ones, right? And also at some point, I want to become efficient and not do this first line that I wrote here, right? I don't really want to have to write out that I'm differentiating with respect to x. I can't even say that. There's a tongue twister. I don't want to have to write out that I'm differentiating with respect to x on the left-hand side, differentiation with respect to x on the right-hand side. It is okay that you write that out, but to be efficient, I'm going to eventually just think through that. And then ditto for the quotient rule. Right? I don't really want to have to write this out, so as I become more competent, more confident, more efficient with the quotient rule, I'm just going to say the quotient rule and write the result here. All right, now I am done with my derivative. However, an instruction and a textbook, an answer in the back of a textbook is going to say find y prime, right? Find dy dx. And so we're going to do some algebra to solve for y prime here. Okay, so bear with me. This is going to get a little tedious and time consuming, but let's go with it. All right. So first of all, I don't like fractions. So I'm going to get rid of the fraction from the very, very beginning. So I'm going to multiply the left-hand side by y squared to get rid of that fraction. Now I'm going to multiply the right-hand side by y squared to get rid of the fraction on the left. Right? So whatever I do on the left-hand side, I got to do on the right-hand side. So the y squareds cancel when I distribute there, and I get just the numerator. The y squared distributes to the 5, and the y squared distributes to this term. On the right-hand side, I got to distribute as well. Y squared distributes to cosine. And then the y squared distributes to this term. All right. Now, I'm going to do what I did in that very first example. Everything that has a y prime, I'm going to bring to the left-hand side of the equation. And then everything that doesn't have a y prime, I'm going to bring to the other side of the equation. So bear with me for a moment as I try to do this in an efficient manner. I don't want to have to write every step down. Right? So again, here's something that doesn't have a y prime. I'm going to subtract that over. Here's something that doesn't have a y prime. I'm going to subtract that over. This doesn't have a y prime. I'm going to leave it. And this does have a y prime, so because it's being subtracted, I'm going to add it over. So this y prime term here is going to stay. This y prime term here is going to stay. And then this y prime term I'm going to add to the other side. All right, and then on the right-hand side, this guy is going to stay. Cosine of x y squared stays. It has no y prime term. And then let's see, this one didn't have a y prime term. I'm subtracting it to the other side. And then this very first term didn't have a y prime attached to it, so I'm subtracting it over as well. So I have gotten all the y primes on the left-hand side. And then the kind of next to last step here, like we saw in the other example, I'm going to take the y prime that's common amongst all three of these terms. I'm going to factor the y prime out. So I'm going to take the y prime out. And then I'm just going to kind of leave the right-hand side alone. Now look, point out to you that I could take a y out of all three of these. I'm not going to bother doing that at the moment. Just discussing ultimately how we get y prime by itself. So now that I have found y prime by itself as a factor, this factor I'm going to divide off. So I'm going to divide to the other side. So I end up with cosine of x y squared minus 5y squared minus y all over that factor of negative x minus 3y squared plus sine of y times y squared. And technically I'm finished there, and there is my derivative y prime for that example. Okay, so I could continue doing example after example after example. I mean, we could spend another hour doing a whole bunch of examples here. And again, I don't like these videos to get too long. We've already spent 30 minutes discussing this. So in my first example, we had a product rule that we did. We had, 6xy. And then in this example, we had a quotient rule that we did. It was x over y. So we could continue to see more and more examples of that nature, where we might have a quotient, we might have a chain rule. And ultimately, the conversation here is, I can't get y explicitly as a function of x, and therefore we have to use the implicit differentiation process. I said this already, but I want to back up and just point this out to you again. When I do the implicit differentiation, there's a kind of mental shortcut. The mental shortcut is, if I'm differentiating with respect to x, or so if I have a variable here that doesn't match the differential operator, then I'm going to take the derivative like normal, which was negative 3y, right? Derivative of negative 3i was negative 3, and then I'm going to multiply by y prime. Here, I have the y variable, and x is my differentiation. So I'm going to take the derivative of cosine, which is negative sine, and multiply by y prime. Okay, so the last thing we want to do in this section is we want to talk about the derivatives of the inverse trig functions. So up to this point, we had talked about derivatives of regular trig functions. We talked about the quotient rule, the product rule. We talked about the derivative of exponential functions. So one thing we haven't discussed is the derivative of the inverse trig function. And the reason that we wait until this moment to have that conversation is the derivation or the proof of this derivative involves an implicit derivative. So for example, let me write it this way, right? We want to find out what is the derivative of inverse sine of x. What's the derivative of arc sine? Or another way to think about this, right? We could say, if y equals inverse sine of x, right? What is dy dx? Right? What is its derivative? So, in order for us to develop this formula, what we're going to actually do is an implicit form. So, here's what I'm going to think of, right? So, if I'm wanting the derivative of inverse sine of x, I don't know how to find its derivative. So, let's write this in an implicit form. So, in other words, how would I get the inverse sine out of this equation? Well, I would use its inverse, right? What undoes the inverse sine function? The sine function undoes the inverse sine function. Right? So the sine of the inverse sine, right, those cancel because they're inverses, and I end up with sine of y equals x. Now, at this point, I'm going to differentiate both sides in an implicit manner. So I'm looking for dy dx. So I'm going to differentiate with respect to x, the left-hand side, and I'm going to differentiate with respect to x, the right-hand side. Now this is going to help me find dy dx, and this is an implicit thought process here. So just like we've been doing, what's the derivative of sine of y? Now again, this is the y variable. We're differentiating respect to x. So there's the implicit piece. So I'm going to differentiate this just like it was normal, right? What's the derivative of sine? That's cosine. And then I multiply by the derivative of the inside, by y prime. And then, I just noticed I have a typo here. You guys didn't stop me. I didn't hear anybody say, hey, wait a second, typo there. So here was the right-hand side, x. I'm differentiating x here. So sine of y equals x. Differentiate the left-hand side with respect to x. Differentiate the right-hand side with respect to x. And my brain was working ahead of myself because the derivative of x with respect to x is just 1. So once I've taken the derivative implicitly, what I have is cosine of y times y prime equals 1. And what we want is the derivative, y prime. So I'm just going to divide the cosine of y over, and there is the derivative of y prime. All right, so we are deriving the derivative for inverse sine of x in this example. Now, since we had y strictly as a function of x, then we want its derivative strictly as a function of x. So in those prior couple examples, we showed that when y is an implicit formula, its derivative will be implicit. But when y is an explicit formula, our derivative we expect to be explicit as well, right? So again, what are we differentiating here? We're trying to find the derivative of inverse sine of x. So if y is inverse sine of x, what is dy dx? So my y is an explicit function of x. I want my derivative to be an explicit function of x. So I have my derivative implicitly. My derivative is not an explicit function. So I need to convert. I need to get this in terms of x. All right, I had to pause the video for a moment there. I don't know if you guys can hear the thunder outside. Maybe you can't. Thunder is really, really loud. I think the math gods are very happy that we are doing calculus today, and they're showering us with lots of rain and thunderous applause. Boom, boom. Get it? All right, so just had a really close lightning strike. Wanted to make sure everything was okay with the computer. So let's finish this off here and figure out how are we going to convert this in terms of x. So this is a little bit of fun, right? This is actually going back to a trig class. So think about what this is saying here, right? What we had from the beginning was inverse sine of x equals y. That was what we were taking the derivative of, right? That was the same thing as saying that the sine of y equals x. So here's how I'm going to interpret this thing here, this equation. This is some angle y, and the sine of that angle is x. Now remember, the sine of an angle is opposite over hypotenuse. So if I think of sine of y equals x over 1, then this angle y in my right triangle has a sine opposite over hypotenuse that is 1. Now if I use Pythagorean's theorem and I do, let's say a squared plus x squared equals 1 squared, and I solve for a, I'm going to pretty quickly find out the other side is the square root of 1 minus x squared. So a squared plus b squared equals c squared. I find what a is, and that's what my other side is. Now, what this drawing allows me to do is say, oh, check it out. I know what cosine of y is, right? Cosine of y is going to be adjacent over hypotenuse. So cosine of y from this triangle is adjacent over hypotenuse, right? Which, of course, I don't really need the 1 in the denominator. So cosine of y is really 1 over square root of 1 minus x squared, right? Cosine of y is really square root of 1 minus x squared. So y prime is really 1 over square root of 1 minus x squared. So officially, what we're saying here is the derivative of the inverse sine function is 1 over the square root of 1 minus x squared. Right, so again, we said if y is inverse sine of x, what is the derivative y prime? Here is our derivative y prime. And so here would be probably what you typically see in a calculus book. So they give you a list of the derivatives of all the inverse trig functions, and here would be the derivative of inverse sine. Derivative of inverse sine of x is 1 over the square root of 1 minus x squared. Okay, so we just did a derivation. We just developed the derivative of inverse sine, and we did that using implicit differentiation. So we could do this for all of the other 6 trig functions, and I don't want to. I don't want to take the time to do that. Right? So ultimately, if we found the derivative of inverse cosine, we would find out is, through that derivation process, negative 1 over the square root of 1 minus x squared. And if we were to do that derivation process, we could find the derivative of arctangent, right? Inverse tangent is 1 over 1 plus x squared. All right, so if we were to continue doing the derivation of all the inverse trig functions, what we would see is what we have down here. I just went on the web and found a website that gave these derivatives and copied and pasted them. Right? So what we see, right, is the first derivation that we did, right, the derivative of arcsine is 1 over the square root of 1 minus x squared. And then we see here the derivative of inverse cosine is negative 1 over square root of 1 minus x squared. Derivative of inverse tangent, 1 over 1 plus x squared. And then we have the derivatives of the other 3 trig functions, the reciprocal functions. We can see cosecant is negative 1 over x square root of x squared minus 1, and then inverse secant, positive 1 over x square root of x squared minus 1, and then inverse cotangent's derivative being negative 1 over 1 plus x squared. So the last thing I want to do in the example here in the video is a couple examples using these formulas to find derivatives of equations that involve inverse trig functions. Okay, so let's say the first example that we want to look at is, let's say we have y equals inverse tangent of square root of x, and we want to find, y prime. We want to find dy dx. So this is not an implicit derivative like we discussed earlier, right? This is an explicit derivative, standard or old normal derivative, because y is defined explicitly as a function of x. So we're just going to take the derivative like normal. Now we know that we just wrote down the derivative of inverse tangent of x is 1 over 1 plus x squared. Now I want to point out to you, I'm going to come back here and erase, or I'm going to write over. This really is a form that the inverse tangent of u is 1 over 1 plus u squared. So I have a chain rule that I'm going to have to do on this problem, right? My u is square root of x. So when I take the derivative of inverse tangent of u, that's 1 over 1 plus u squared. So I'm going to have 1 over 1 plus the u squared. And then the chain rule says I have to multiply by the derivative of the inside. Right, so I have to multiply by the derivative of root x. Right? So of course this is 1/2 x to the negative 1/2 is what this derivative is going to be. So I have 1 over 1 plus, and then root x squared is just x. And then times this guy, right? So the 2 is going to stay in the denominator, and the root x gets pushed into the denominator as well, right? So I really have a 1 over, and I'm going to say 1 plus x, and then I really have 2 root x in the denominator from that other fraction. And technically there's my derivative. I am done with my derivative. I guess I could do something crazy like take the 2 root x and distribute to each of these. At this point, I'm not going to bother doing that, and there is y prime. Let's say that we look at another example here, and I'm going to make some stuff up here. So we have y equals e to the x inverse sine of x. I want to find dy dx. Let's find y prime. So here's a product rule. So I'm going to do derivative of the first. Derivative of e to the x is e to the x times the second, and then plus the first, and then derivative of the second. So the derivative of inverse sine was 1 over square root of 1 minus x squared. So there we are doing a product rule involving inverse sine and e to the x. All right, let's do another example. Let's say we have y equals arc cosine of, let's say, x cubed. Again, remember this is inverse cosine, just in different notation. So we're going to do y prime. So I have a composition here. Inverse cosine is the outer, x cubed is the inner. So the derivative of, all right, I'm going to rewrite this over here, right? We had inverse cosine's derivative being -1 over the square root of 1 minus x squared. Again, I want to point out to you that the x is really a placeholder. Inverse cosine of u is -1 over the square root of 1 minus u squared. So in this case, my u is the cube function. So the derivative of inverse cosine is going to be -1 over the square root of 1 minus my u squared, and then times the derivative of the inside. So the derivative of the inside is 3x squared. So when I simplify this, right, the 3x squared goes up into the numerator, and then in the denominator, I'm going to go ahead and square x cubed, and that gives me x to the 6th. There's y prime for that example. Okay, let's do one last example here, and let's say that we want, in this example, we want to find the equation of the tangent line to, let's pick inverse tangent of x at x equals 0. All right, we've been finding equations of tangent lines quite a bit in all of our prior videos. So to find the slope of the tangent line, we need the derivative. So I need to find y prime. So the derivative of inverse tangent is 1 over 1 plus x squared. So then the slope at x equals 0, right, is y prime at 0. So we're going to see if we plug 0 in here, we're going to get 0 squared plus 1. So we're going to have 1 over 1, or 1 is the slope at x equals 0. And then I'm going to do the point slope formula. Y minus y1 equals m times x minus x1. So I have my slope, m. I have my point. I don't have the y value. I have the x value. I don't have the y value. So I have y minus I. I'm going to come back and figure that out. And then m and x minus 0. So what is the y1, right? So our equation was inverse tangent of x. So my y is inverse tangent of 0. So, in other words, right, what do I take the tangent of to get 0? I could look on a unit circle and answer that question. I could use my calculator to answer that question, and we're going to find out that this is 0. So inverse tangent of 0 is 0. So I have in my tangent line y minus 0 equals 1 times x minus 0, and we get y equals x as the equation of our tangent line. And then what I want to do here real quick is let's graph to check our work. All right, so I typed in y equals arctan of x, and then I typed in the tangent line y equals x, and we can see at x equals 0 here that y equals x is tangent to the arctangent function. Okay, so that's everything I want to cover in this video. I look forward to seeing you guys in the next video.